Very much for joining us today. My name is Giulia and I am Chief Data Scientist at Hive Power, where I'm responsible for designing and developing machine learning-based applications for the energy business. I'm a greedy user of the Python connector and I can say that I'm extremely satisfied with it. It's flawless, very easy to use, and well documented. And more importantly, when I had some questions, the support team of Meteomatics was super quick to respond, so that was really nice. At Hive Power, one of the main products that we created and continue to develop is the Flexibility Orchestrator. This tool orchestrates the operation of a pool of different assets that can be remotely controlled. The Flexibility Orchestrator can optimize multiple business objectives and improve the performance of the aggregator without affecting the comfort of end users. For example, some controllable assets are electric vehicles, charge and discharge, including the vehicle-to-grid business model, heat pumps and air conditioning, storage batteries, electric heaters for domestic hot water, and in general, any industrial load that can be shifted in time. Now, the Flexibility Orchestrator is obviously more effective when it is informed by future predictions of energy demand and generation. For example, imagine that I predict a particularly high peak of energy demand at some time tomorrow, when the energy is billed with a higher tariff, so it would cost me more. Then I can pre-charge a battery using renewable energy sources and then discharge the battery during peak hours to cover part of the demand. This way, I reduce my costs. For this reason, we built a forecasting tool that serves exactly this purpose. It predicts aggregated energy demand and photovoltaic energy generation in the short term using a data-driven approach. So our forecaster uses machine learning techniques and is informed by a plethora of data. As you can imagine, weather conditions strongly influence energy demand and photovoltaic energy generation. And because weather is so important here, at Hive Power we spent quite a bit of time to evaluate and select the best weather forecast provider. We assessed about a dozen providers and Meteomatics was by far the best under all aspects. Apart from the accuracy of their numerical weather predictions and the ease of use of their API, we chose Meteomatics because they are one of the few providers that allow retrieval of past weather forecasts. For our application, in fact, it is really important to train the machine learning algorithms on the same data that they will see at inference time. In fact, if I use past weather observations as opposed to forecast to train the model would put a certain amount of trust on the weather parameters. However, at inference time, I would have no other option than replace observations with forecast. And even though Meteomatics forecasts are excellent, they're not absolutely correct 100% all the time by definition. They're not perfect. And in this case, the model would put too much trust on the weather parameters and the results would be less accurate than if I trained the model on weather forecast in the first place. Now I'm going to demonstrate what I just said. I'll walk you through a practical demonstration of our forecaster and show you what happens in two cases. When we train the predictive model with weather observations and when instead we use weather forecasts. For this tutorial, I will present a use case of one of our clients, AMB, the Azienda Multiservizi Bellinzona, a Swiss distribution service operator. Every day, our forecaster generates a day-ahead prediction of the aggregated electricity demand of AMB. You can see a sample of this prediction in the middle chart. It's a probabilistic forecast of energy demand here. Based on this prediction, the Flexibility Orchestrator finds the optimal operation of a hydropower plant for peak shaving. Finally, based on the prediction and the scheduled hydropower generation, our smart pricer computes a dynamic energy tariff for the next day. This is a pioneering opt-in tariff for residential users. Traditional low and high tariffs have a fixed schedule, typically low at night and high during the day. Instead, this dynamic tariff applies low and high prices according to the expected effective peak hours. So it can happen that on a sunny day, the tariff is low around midday because the algorithm predicts significant photovoltaic generation that will cover most of the demand at that time, or because the hydropower plant is supplying energy at that time. Residential users can look up the next day tariffs on a dedicated mobile app. Okay, so time to jump into the code now. I prepared a few notebooks to demonstrate the functionalities of our forecaster. So first of all, we're gonna pip install the repo that contains the code of the forecaster. This is private code, it's proprietary of Hive Power, so you're not gonna find it on GitHub. After the installation, we import some raw data as sample data. First of all, we got the power signal, so the target that we're gonna try to predict, that's the load, the demand of AMB. Then we got the weather forecast data from Meteomatics. In this case, I simplified a bit and I'm just using 4 weather parameters. We got the temperature, the global solar radiation, the relative humidity, and the precipitation. The forecaster expects another 16 parameters that we're not going to use here, so I just set them to null in the pandas data frame. Then we got holidays data, public holidays, and school holidays. A bit of configuration for the dynamic settings. These are the parameters of the model. And now we can build a data set, which simply means just joining together the different data sets that I showed before. So power, weather, and holidays. We got some convenient functions that do this for me. And basically the result is a big table indexed by time with many different columns. The first one is the target that we want to predict. The load, here you go, and I'm gonna show it here in a time series chart. Okay, so it's 3 years of data. The data is 15 minutes sampled, and what we're gonna try to do is to predict the demand of the next day. Okay, assuming that we have historical data up to yesterday, so up to midnight. Okay, and because it's 15 minutes sample, it means that we're gonna predict 96 values, so the 24 hours of the next day. And every day we do this, and so on and so forth. We got the temperature plotted here in the second graph, the global solar radiation, the relative humidity, the precipitation, the public holidays, and the school holidays. The last 2 are binary signal. Then we do some feature engineer, so we build new features based on the existing ones, and some of these new features express the seasonality of the time series. So we've got the time of the day of the week of the year, the month, the year, and the time of the week. Okay. Now we're going to split the whole data set into 2 parts, a train and validation set and a test set. So the last year of the data set is the test set. The rest is train and validation. And what I'm going to do is I will train the forecaster model in a 5-fold cross-validation. So I will rotate the train and validation set, but I will keep the test set fixed. Okay. And for this exercise, I'm going to use the forecaster with backend of LightGBM. LightGBM is a gradient boosted tree algorithm. Okay, so easier shown than said. We start with the first fold, and this image shows the split between train, validation, and test. So green and blue are the training and validation set, and the test set is the red. Okay, and in the train and validation split, I keep whole days all together. So a day can either belong to the training or the validation set. It can be split. Okay. I run the training. It will stop with early stopping to avoid overfitting. And then I'm going to calculate the accuracy matrix on the test set. So we got a mean absolute error of about 474 and a mean absolute percentage error of 5.4% on this fold on the test set. And now I keep doing the same for the other 4 folds. So there will be the second, the third, the fourth, and the fifth. Same logic. And eventually I will end up with 5 different models that I'm going to combine together with a simple average in an ensemble to predict the ensemble model of the test set. The metrics of this ensemble model on the test set are a mean absolute error of 440 and a mean absolute percentage error of about 5%. Okay, now the question is, what happens if I train my model on weather observations and run the inference based on weather forecast? Let's do the exercise, let's see. So I'm just going to do exactly the same I did before. So pip install the repo and then load the same power data. Load the weather forecast data from Meteomatics, those 4 weather parameters I explained before, fill up with nulls the other columns. But then I'm going to replace some of the weather forecast with weather observations. And I'm going to do this in the first 2 years of the set, so in 2018 and 2019. And I'm going to keep the weather forecast in 2020, which will be the test set, as you saw before. Okay. So now we have this combined weather data set, again, the same holidays, same settings for the algorithm, including the random state of the all functions that have a random behavior, so the model is deterministic. We build the data set in the exact same way, and the results are going to be really similar, but not exactly the same as before, because we replaced those 4 columns with partially with observations. Okay. Same feature engineering, the rest is all the same. And now I'm gonna just run the same training with 5 folds. Let me just get to the end of the notebook, and I'm just gonna show you the results, the final results. So the results are summarized here in this table. We got 5 sets of validation, so the 5 folds, and the last one, 6th, is the test ensemble matrix. So the first column shows the mean absolute error when we use weather forecast consistently at training and at test time. And the second column shows the situation in this notebook when we replaced weather forecast with weather observations at training time, but not at test time. Okay, so the mean absolute error, the lower the better. Okay, it's consistently better in all validation folds as expected, because observations are perfect by definition. Okay, and so the model puts a lot of trust on these observations, and then when it goes to test time, to inference time using weather forecast, the situation reverses. So we got a better metric for the forecast case and a worse metric for the observation case. The mean absolute error in the forecast case is 440. It gets about 489 when we use observations at training time. And the mean absolute percentage error goes from 4.98% to a 5.45%. Lastly, I would like to show you the forecaster at its full capabilities, at its full potential. Okay, so we're gonna use all 20 weather parameters from Meteomatics, and we're gonna optimize the hyperparameters of LightGBM. So again, in this notebook is exactly the same. I pip install the repo and I load the same data. This time I use all 20 weather parameters from the weather forecast. And I use optimized hyperparameters for LightGBM. I run a search in advance here. The rest is exactly the same. Build the data set, run the feature engineering, and the training in 5 folds, exactly the same. Let me just get to the results and I'll show you how the metrics improve on the test set in this case. So the new columns are here. We got the mean absolute error and the mean absolute percentage error of the full forecast training. Okay, and we see that the mean absolute error drops from 440 from the first exercise when we had just 4 weather parameters to 418, so quite a significant improvement. And you can see it also in the mean absolute percentage error. It goes from 4.98% to 4.71%. So that's great. In addition to this, we can also have a look at the feature importance computed with the Shapley values. Consider that the model in the end digests about slightly less than 1,000 features. So here I'm showing just the 50 more important features. And you can see that among these, many weather parameters appear quite frequently, so they are important in the model. Last thing that I can do with the forecaster is to train a probabilistic model as opposed to a point forecast. What I showed before was a point forecast, so the model predicts the most likely value of the signal at a certain time. With a probabilistic model, I get information on the whole distribution of the forecast. We do this using the algorithm quantile random forest as a backend. And let me just get to the end of the notebook and show you a sample of the results. Here is basically what you get. So you get prediction intervals, okay? And they can be interpreted as basically confidence intervals of the model in this case. And so they're really useful in applications like peak shaving when you need to know with a certain amount of confidence when the peak will happen the next day. That's all from me, so thank you very much for your attention.